Welcome to Lesson 5 of the GAMS training. The objective of this fifth session is to improve programming skills. In particular, we will learn new commands, we will define different types of variables, we will introduce constraints on variables, and we will run simulations. We start with the set syntax. We start with a quick reminder on the syntax for defining simple sets. If you recall, we start with the keyword sets, followed by the set name and explanatory text. Then, between slashes, we list the set element names, each followed by explanatory text. The elements can be separated by a comma or by an end of line, as in this example. We close the statement with a semicolon. Again, explanatory text shown in italic is optional, but strongly recommended for documenting purposes. Recall that keywords set and sets are equivalent. So this statement is equivalent to this statement. We can either write statement using the plural sets or the singular set. Sets can be defined in one statement or under separate set statements. So we can define the sets I and j in a single set statement or in two separate statements. But remember to end each statement by a semicolon. When a set includes a sequence of elements, the asterisk can be used with the beginning and end of the sequence to simplify the writing. Take the two following examples. In the first one, we have a sequence T of years from 2000 to 2005. And in the second example, we have a sequence X of terms containing both a letter and a number. We can simplify the writing of these sequences by inserting an asterisk between the first and last element of the set. Note that in both cases, the numbers must change sequentially. You might sometimes want to work only on some elements of a set. We can define a subset in the following manner. The set I contains element A, B, and C, and the set K contains only the element A and B of set I. Note that when defining subsets, the order is important. The largest set from which the subset is derived must be defined prior to the subset. The subset must include in parentheses the set from which it is derived. We can also define a complementary subset with a single statement. First, we define the set and subset as shown previously. We add a subset CK, which contains the element of I that are not in K. The set CK is declared without element listing. Instead, we use the GAMS keyword not to assign to CK the elements of I not included in K. Subsets are useful when we want to assign different behaviors or values to the elements within a set. For example, let I be the set of all commodities and a subset Agri containing all the agricultural commodities. We also define a subset non-agri which contain non-agricultural commodities. As previously, we define non-agri by using the complement assignment. Now let's assume that we want to apply a 15% tax on non-agricultural commodities. To do so, we first add to our set definition above a parameter statement. We declare this parameter, which we call Tx, on the complete set I. Now we apply the different values of the tax to the two subsets defined. No tax on agricultural product but a 15% tax on non-agricultural products. Next, we will learn to use another set statement, Alias. This statement allows the user to give different names to a previously defined set. Let's define the sets I and j. The syntax for the alias statement is the keyword alias, followed by the name of the set, as previously defined, followed by various other names. All the names are separated by a comma and closed in parentheses. The statement ends with a semicolon. The statement indicates that the set ij includes the same elements as set I, and both names can be used indifferently. This statement indicates that set k and m include the same elements as set j, and all three names can be used indifferently. Note that the primary set must be defined first before using the alias statement. Having multiple names for one given set can be useful for multi-dimensional parameters and variables, such as input-output tables. We define the set I, which include the three sectors: agriculture, industry, and services. Using the statement alias, the set I is given a second name, ij. Now we define an input-output table, io, on I and ij, meaning that column titles will be identical to the row titles. Another tool used on set definition is the mapping between elements of different sets. It can be very useful in GAMS, as we shall see in advanced lessons. Let's start with a simple one-to-one mapping. We define two sets. Set A contains cities. Set B contains countries. We define a mapping between elements of set A and elements of set B as a subset that matches the capital cities with their corresponding countries. The name of the subset C is followed by the two sets from which it is derived, A and B, in parentheses and separated by a comma. The listing of elements, as for other sets, is enclosed between slashes and separated by a comma or an end of line. Each element is a combination of an element from the first set A and an element from the second set B, separated by a dot. The order of the match must correspond to the order of the sets, first the elements of set A, followed by the element of set B. When we display set C, we obtain a logical table with set A as rows and set B as columns. The keyword yes signals that the corresponding columns and rows are matched. We can also have many-to-one mapping between elements of different sets. We have added to the set A the city Nice, and we want to map cities to the corresponding countries. The definition of the sets is similar to the previous one, but now note that the first element of set D maps the two cities, Paris and Nice, to France. In this case, the first term of the match, the two cities, Paris and Nice, are in parentheses and separated by a comma. They are linked to France by a dot, as before. When we display set D, we obtain a logical table with set A as rows and set B as columns. But now, the keyword yes signals that two rows are matched to the column France. We can also have one-to-many mapping between elements of different sets. In our example, we define another subset E, but instead of mapping A to B, we map B to A. In other words, we want to map the countries to the corresponding cities. The definition of the sets is similar to the previous one, but now note that the first element of E matches France to two cities, Paris and Nice. In this case, the second term of the match, the two cities, Paris and Nice, are in parentheses and separated by a comma. France is linked to them by a dot, as before. When we display set E, we obtain a logical table with set A as columns and set B as rows. But now, the keyword yes signals that two columns are matched to the row France. Next, we looked at operators for sets. Each element of a set has a relative position in that set. The OR operator returns that specific position. For example, we define the set I with three elements A, B, and C. We also define the parameter x over the set I. We then assign to each element of x its corresponding position in the set I by using the operator OR. If we display the parameter x, we would have the following result. The element of x have the corresponding values. 1, because A is the first element of set I. 2, because B is the second element of set I. And so on. Another set operator is card. This operator returns the number of elements in a set. So again, we define the set I having three elements, A, B, and C. We define the parameter y and assign to y the number of elements in the set I using the operator card. Y will take the value 3 since there are 3 elements in set I. Next, we will review variables and constraints. As you may recall, the basic syntax for declaring free variables is as follows. The keyword variables is followed by a list of variables separated by a comma or an end of line. The variable names are followed by the set or sets on which they are defined in parentheses and separated by a comma if more than one set. The explanatory text follows each variable and the statement ends with a semicolon. Again, items in italics are optional. There are many types of variables, and each one can be identified using specific keywords in the declaration statement. The following table associates the type of variables with its corresponding keyword. For continuous variables, we can use the keywords free variables or variables. In the case of free variables, if you recall, by default, in GAMS, variables are free. We can also use the keywords positive variable for variables that can only be positive, and negative variables for variables that can only be negative. For discrete variables, we can use the keywords binary variables or integer variables. By default, GAMS assign bounds to each variable type as shown in the following table. The user can change these bounds except for binary variables, which can only be equal to 0 or 1. We can define positive and negative variables as free variables and then assign to them a lower or upper bound. So in the next statement, we define first 3 free variables using the keywords variables, and then assign a lower bound of 0 to the positive variable and an upper bound of 0 for the negative variable. This is equivalent to defining the variables using specific keywords in the variable statements. In practice, it might be preferable to first declare all positive and negative variables as free variables and add bounds when necessary. Both binary and integer variables are discrete variables. Binary can only take the value 0 or 1. By default, integer can only take values from 0 to 100. The user can set other bounds. A variable can be set as exogenous in different ways. You can define the variable as a parameter and assign a value. For example, we define the parameter x and assign the value 10 to it. Or you can define it as a variable and fix the variable. For example, we define the variable x and fix the variable to 10 using the suffix .fx. The fx attribute sets the lower and upper bound at the same value. So the variable x can be assigned a fixed value by a single statement using the suffix .fx, or by two statements using the lower and upper bound attributes. At this time, we like to point out the difference between how economists and GAMS view exogenous variables. Economists tend to distinguish parameters from exogenous variables. Exogenous variables are usually associated with variables that are not explained by the model, in contrast with endogenous variables that are determined by the model. Parameters often refer to behavioral characteristics. GAMS treats both parameters and fixed variables in the same way. In other words, GAMS does not change the value of fixed variables while solving the model. And on the other hand, the value of free variables changes when solving the model. Another important attribute of a variable is its level, .L. The value of the level is not fixed and changes after the model solution. The user can initialize a variable prior to solving the model. By default, a variable initial value is 0. Variables may be constrained either by using bounds, as we have seen, or they can also be constrained using equations. Consider the following constraint, which sets the variable x to 15 or below. In GAMS, we could define x as a variable and set an upper bound of 15 using the suffix .up. This would be equivalent to defining an equation that we call constraint, for example, and set the upper bound by using the relational operator equal L equal. Taking another example, we can express that y is greater or equal to 0 in two ways. By defining the variable y and setting its lower bound, or by using the equation definition constraint and the relation operator equal g equal. Finally, we can express that z is equal to 100 by defining a parameter z and assigning the value 100 to it, or by defining a variable z and fixing its value at 100 using the .fx attribute, or a third way by defining the variable z and an equation called constraint using the relational operator equal e equal. However, when the constraint involves more than one endogenous variable, then the only way it can be written is through an equation. For example, to express that x is lower or equal to z, we first define the two variables x and z, and an equation which we call constraint, and write the relation between the two variables using the operator equal L equal. Next, we present an optimization problem. To illustrate potential applications of what we have covered so far, we present an example of an optimization problem developed by David Laborde. In this problem, we assume that a consumer at McDonald's wishes to minimize his expenditures subject to the following. He must fulfill his daily requirement of nutrients, at least 2,500 calories and 65 grams of protein, and he must choose at least one item in the menu from each category. In other words, he must select at least one main course, one beverage, one side, and one dessert. Which items should the consumer select from their menu to minimize its total expenditure? In the following menu, each item is attributed a price and nutritional contents in terms of calories, protein, and fat. The items in the menu have been classified in 4 categories: main course, sides, desserts, and beverages. We can write the problem in mathematical terms. We want to minimize total cost. Cost is expressed as the sum of all items consumed times their price. And where Q is the quantity of items consumed, P is the price of each item in the menu, and product is the set of all items in the menu. So we want to minimize this cost subject to satisfying a daily minimum intake of nutrients. Minimum intake is the daily minimum requirement of nutrients in terms of calories, protein, and fat. Intake is the nutrient intake from consuming items on the menu. And Nutri is a set of nutrients, calories, protein, and fats. The daily nutrient intake from consuming items on the menu is given by the sum of all items consumed times their nutrient content, where content is the nutrient content of each item. We will follow the typical structure of a GAMS program as seen in Lesson 2 to solve our optimization problem. Recall that first we need to define the sets. We have 2 sets. The first one, which we call product, contains all the items on the menu. The second set, which we call Nutri, includes as elements the nutrients, calories, protein, and fat. Items on the menu are classified in 4 categories: main course, sides, desserts, and beverages. We express these groups by defining subsets. We define the following subsets. Main contains the items and the main course in the menu. Sides contains the items and the sides in the menu, and so on for dessert and beverages. All the subsets are derived from the set product, which lists all the items on the menu. Next, we define the parameters. We know the following for each item: the price, the nutrition content, and finally, we know the minimum daily requirement. We therefore have 3 parameters, and they can be treated either as parameters or as fixed variables. We will use both types of definition to illustrate what we have just learned. P and content will be defined as parameters, minimum intake as a fixed variable. P is defined on the set product. It has 1 dimension. First, the keyword parameters, followed by the name of the parameter P, and the set on which it is defined, product. Explanatory text is added for documentation. We assign values to the various elements of the parameter in the same statement. All the elements of the set are listed followed by their corresponding price. They are enclosed within slashes. So in one statement, the parameter P is declared, given a name, and defined, given a value. The second parameter, content, is defined on two sets, product and Nutri. It has two dimensions. We use the table format, and in one statement, we declare the parameter and assign values to its elements. Product being the first set, it represents the rows. Nutri being the second set, represent the columns. We are now ready to declare the variables. They are: intake is a variable that must be positive. Mean intake is an exogenous variable not determined by the model. We declare it as a variable, but we fix the values given to the variable. Both intake and minimal intake are defined over the set Nutri. Cost is the total cost of the meal. It has 0 dimension. Finally, Q is an integer since it is not possible to purchase a fraction of an item. We use integer variable as a declaration heading. It is declared on the set product and it has 1 dimension. We now declare and define the equations. They are: equation intake. This equation computes the total nutrient intake, denoted by intake, by summing over each item nutrition content. Equation cost. This equation computes the total expenditure cost of the meal. It sums over the unitary cost of each item. Finally, equation constraint 1. This equation expresses the nutrient constraint that requires total intake of nutrients to satisfy a minimum requirement. We have other constraints on the content of the meal. They require that the meal must include at least 1 item from each category. So we declare 4 constraint equations, 1 per category. The constraints will state that the sum of items consumed must be greater or equal to 1 in all 4 categories. Note the use of different parentheses, round, brackets, and braces. They are all equivalent as long as opening and closing symbols match. Now, the only thing left to do is to declare and define the model. In the declaration, we name the model Nutri1 and we add explanatory text. Since we want all the equations to be included in solving the model, we use the keyword all between slashes. A semicolon ends the declaration. We are now ready to solve the model. We use the solve statement followed by the name of the model. Recall that our objective is to minimize the cost, so we use the keyword minimizing and specify the objective function cost. Finally, we specify the solver we want to use. Again, we encourage you to consult the user's guide for a complete list of solvers and the problems for which they are best suited. In our case, the presence of discrete variables makes the solver MIP best suited for our needs. We have completed the model. Once you have written the model in GAMS IDE, you can run the model simply by clicking on the red arrow button in your task menu or by pressing F9. Before looking at the result, check the solve summary in the list file to verify that the model ran correctly. The solver status should read normal completion. The model status should read integer solution. If you have encountered some errors in writing the programs, we refer you to Lesson 4, where you have learned to detect and correct errors in GAMS. If your model is error-free, you can now check the solution variable section of the list file and check the solution values of the variable intake. Click on the plus sign next to the solution variable header in the left panel of the list file to reveal the list of variables. Double-click on intake. You can see the nutrients consumed. 2,530 calories, 76 grams of proteins, and 93 grams of fat. Next, double-click on the variable cost. The total cost for this meal is $12.60. The next variable is Q, the quantity of each item consumed. The meal will include 5 hamburgers as a main course, 1 large fries as a side, 1 McFlurry as a dessert, and 1 Coke as a beverage. This combination will minimize total expenditure while fulfilling the minimum daily requirements of nutrients. So the quantities that would minimize total cost while fulfilling daily nutrient constraints are 5 hamburgers, 1 large fries, 1 McFlurry, and 1 Coke. Of course, these results are in part driven by the prices given for each item on the menu. If we were to change the prices, the solutions would change. Let's assume now that the price of a hamburger increases by 20%. How would such an increase change the composition of the meal? We want to run a simulation that will do just that. Simply add the 2 lines shown below at the end of the program. After the first solve statement, we change the price of a hamburger by an assignment statement, which increases the price by 20%. We include the second solve statement, identical to the first one, but now the model will solve with a new price. Run the model as before. If the model ran correctly, you should see the following in your list file. The section in the left panel will appear twice. Once for the first solve before the shock at line 134, and once for the second solve after the shock at line 137. To see what impact the price increase has on the solution, go to the end of the left panel in the list file and open the second solution variable by clicking on the plus sign to reveal the list of variables. Click twice on cost. We would expect that a price increase on any item would increase total cost, and it does. It is now $13. We also expect that the composition of the meal based on the solution values of the variable Q would change. The optimal combination now would be 3 cheeseburgers, 1 large fries, 1 McFlurry, 1 milk, and 2 Cokes. We have now completed Lesson 5 of the GAMS training, and for your assignment, write the GAMS code that was presented to you in this lesson. Don't hesitate to test your knowledge by trying different ways of coding the model. Next, verify that it runs properly and that you obtain the same results. Again, this is an opportunity to learn how to detect and correct errors if you have opted to write the model differently. Finally, run 1 or more simulations by trying various changes and compare the simulation results with the base solutions.